Welcome back, everybody. We are now ready to study realistic cosmic inflation. And for that, let us begin by studying how an early phase of almost exponential expansion could have come about. What caused it? To that end, let us zoom out and look at the big picture. Let's look at the full action of nature, the whole thing. The action can be written in this way, I mean, as far as we know it now, right? It starts out with a cosmological constant, just because in principle it's allowed. It doesn't conflict any evidence. In fact, we have some evidence that there is a finite cosmological constant at work at the moment and making our universe accelerate. Not at a particularly strong rate, but still it's accelerating. Also, there is the Einstein-Hilbert action. And then we expect that there ought to be higher order curvature terms, again, because the theory allows it, but we do not have any evidence for the existence of such higher order curvature terms. They would be suppressed anyway, naturally. If you look at the higher order terms and you put prefactors there in terms of the gravitational constant, such that the units come out right, then these higher order terms will be very, very small. It's the same reason for why the cosmological constant should canonically be expected to be tremendously large. If this has a reasonable prefactor, then that would have to be very large, and these would have to be very small. Okay, so that is the gravitational part of the action, but the action goes on. There is also the action of a scalar field. We know that there's at least one scalar field in nature, that of the Higgs particle, but the standard model of cosmology holds that there's also another scalar field in nature, the inflaton particle. So it has the usual scalar field action and some potential. There is some speculation that the Higgs field might be the inflaton field, but it's not a good match. And then there are all the other fields of nature, for quarks, for gluons, for photons, and so on. For the purpose of very early universe cosmology, we can neglect the action for the other fields for reasons that we will discover a little later now in this lecture. And as well, we will neglect those terms. It's not clear that it is legal to neglect them for the very early universe, for the description of the very early universe. The reason being that in present-day physics, these terms do not seem to matter at all. But at the beginning of the universe, all bets are off. These things might be important. But we have no evidence positively that they are important, so we drop them by Occam's razor. The potential could be anything for the Klein-Gordon field that describes the inflaton. We don't quite know the potential function. One example might be this, just the phi to the 4 theory. But many other potentials are consistent with observations. The data are giving us some evidence about some particular part of the spectrum, as we will see later in this lecture today. But the full, sorry, not the spectrum, of the experimental observations in cosmology give us, on the basis of the standard model of inflation, some evidence about some stretches of the potential V, how it will behave, but the evidence does not tell us what V of phi is for all phi. Now, given this action, what are the equations of motion? Well, the equations of motion are obtained, as usual, by differentiating with respect to a field and setting the variation equal to 0. This will give us the classical equation of motion, but in fact, after quantization, we expect the same equations to hold, but for operator-valued fields. So in particular, we obtain the Klein-Gordon equation, where gravity enters in various places. You remember the D'Alembert operator here. This is what we obtain, the Klein-Gordon equation is what we obtain by functionally differentiating the total action of the standard model with respect to the inflaton field. If we, on the other hand, functionally differentiate the total action of the standard model with respect to the metric and set that equal to 0, then we obtain the Einstein equation. And just like in the Klein-Gordon equation, the metric snuck in and is, making itself felt in the evolution of the Klein-Gordon field. Similarly, here for the Einstein equation, it's true that it's not only about the metric, but the other fields sneak in as well. And how they do it is through the energy momentum tensor. All fields, including the Klein-Gordon field, all fields have an energy momentum tensor, and that contributes on the right-hand side and therefore couples to curvature. So the matter fields, such as the Klein-Gordon field, are coupled to curvature through the metric, and the equation of motion of the metric also has a coupling to matter through the energy momentum tensor. Now, the energy momentum tensor has contributions from all kinds of particle fields, and the contribution to the energy momentum tensor from the Klein-Gordon field, from the inflaton field, is given by this expression here, which is the functional derivative of, if you don't remember, the energy momentum tensor is obtained by functionally differentiating the matter part of the action with respect to the metric. The Einstein equation has two parts, a left-hand side and a right-hand side. It's this equation, the Einstein equation, is this equation. And S has a gravity part, the Einstein-Hilbert action, cosmological constant, and it has a matter part, the action of, photons, quarks, inflatons, and so on. And so this is really the sum of two derivatives here. The derivative of the gravity action with respect to the metric, that gives us the left-hand side, and the derivative of the matter part of the action with respect to the metric, and that gives us the right-hand side. Okay, so the total energy momentum tensor here, in nature, contains the energy momentum tensor of a scalar field, or the scalar fields, and contributions from other fields. Quarks, gluons, photons, and so on. But as we will see in a moment, those don't contribute that much, not in the very early universe. There's something special about the contributions from scalar fields that the other fields don't have. And that special thing makes the energy momentum tensor contribution from scalar fields dominate over the energy momentum tensor contributions from the other fields. So we will later have reason to neglect that part. I did not write down the other equations of motion that you would obtain by functionally differentiating the total action with respect to the electromagnetic field, the gluon field, and so on. They would just be the usual Maxwell equations or Young-Mills equations and so on. But as I said, these other matter fields likely did not contribute significantly in the very early universe because they didn't contribute much to the energy momentum tensor. Now, to solve all those equations together is very difficult, highly nonlinear. So to get a first handle on what is going on, we will make as a zeroth order calculation, we will make a dramatic simplification. Let us look at the simplified special case where we have complete homogeneity and isotropy. If we do that, then the inflaton field is only a field that depends on time but not on space, because we assume it to be completely constant in space. Not in time, but in space. So it's isotropic and homogeneous, so it's constant in space. So the inflaton field only depends on time in that very, very simple approximation. And the metric, too, we assume to depend only on time, but not in space. It's not so bad, that approximation. The universe is really quite homogeneous at length scales of 1 billion light years and over. and isotropic. Another way of looking at that simplification is to say that we're looking at the zero mode only. See, the zero mode of a field is the constant part of it. So with the assumption of homogeneity and isotropy, in other words, that there's no space dependence, that there's only time dependence, then the equations of motion that we have to solve simplify quite a bit. The Klein-Gordon equation simply becomes this equation. And notice it has only time derivatives in it, but no space derivatives, because there is no space dependence anymore. And there's still this friction term here. Now let us calculate the impact of the Klein-Gordon field onto the Einstein equation. So for that purpose, we need to calculate what energy momentum tensor contribution the Klein-Gordon field will give us. Turns out that the 0,0 component of the energy momentum tensor, which is also called the energy density, rho of t, is, when you calculate it, just plug it into the formula that we had earlier for the energy momentum tensor of a Klein-Gordon field. It is 1/2 phi dot squared plus the potential of phi, and the space-space component of the energy momentum tensor, which is also called the pressure, is 1/2 phi dot squared minus the potential of phi. Those two expressions then go into the right-hand side of the Einstein equation, or I should say that the off-diagonal elements are 0 for the Klein-Gordon energy momentum tensor. So the energy momentum tensor of the Klein-Gordon field now goes into the right-hand side of the Einstein equation, and that's what we obtain. The Einstein equation, which is an equation that is tensorial, then simplifies to just two equations. There is the 0,0 component of the Einstein equation, and the 0,0 component of the Einstein equation just becomes that. And then there are the space-space components, II components of the Einstein equation, and they become this. So these are the generalizations of these two equations. So this is much more complicated. That would be the full Klein-Gordon equation, full Einstein equation. But if you assume isotropy and homogeneity so that there's only time dependence left over, then all the space derivatives in this business drop out. All the functions become only functions of time. Only time derivatives survive. And we are left with these three equations. The Klein-Gordon equation, the 0,0 components of the Einstein equation, and the II components of the Einstein equation, where here we do not have a summation. This equation is true for every I individually. So what are the unknowns in this business? Well, we want to calculate what A of t is, the expansion of space-time, and we want to calculate what phi of t is. How does the Klein-Gordon field evolve over time? And here we have the equations that will determine that. So in principle, if you specify the theory, if you specify the action, and the only thing that needs still specification is the potential V of phi. So once you've specified what V of phi is, and you give initial conditions for the scale factor and for the Klein-Gordon field, then you can just plug that into these coupled ordinary differential equations and numerically solve for the evolution of the scale factor of the universe and the amplitude of the scalar field, in a way that would take everything into account, the back reaction to all orders. We did not make any approximations other than there is no space dependence. So the inflaton field affects, through its energy momentum tensor, the expansion of space-time, but vice versa, the expansion of space-time has an impact on the evolution of the Klein-Gordon field. So it goes both ways. A system of coupled equations there. Now, let us look at the role of the cosmological constant in these equations here. Remember, these are the equations of motion. Klein-Gordon equation, 0, 0, and II components of the energy momentum tensor. And these are just this is just spelling out what the energy momentum tensor's components are in terms of the Klein-Gordon field. So these are the things that go into here and there. Now, what is the role of the cosmological constant in this? We see the T naught naught occurs together with the cosmological constant here in the 0, 0 component of the Einstein equation, which means that you can achieve the same thing as far as curvature is concerned, as far as space-time's expansion is concerned. You can achieve the same thing by either, let's say, increasing T naught naught or increasing lambda. The equation doesn't care if there's an increase, whether it is from this or that. In other words, the T naught naught plays exactly the same role as the lambda. T naught naught is the energy density. In other words, lambda, the cosmological constant, contributes to the Einstein equation here, to the 0, 0 component of the Einstein equation, in exactly the same way as a positive energy density would. So I'm not saying that the cosmological constant is a positive energy density, but it contributes to the dynamics of space-time in the same way as if it were a positive energy density, as if it were a positive contribution to T naught naught. I'm assuming here that lambda is positive. On the other hand, we have the II components of the energy momentum of the Einstein equation. And here we see TII is the pressure. Here we see that the pressure contributes to the dynamics of space-time, and the cosmological constant now contributes with the opposite sign. So I'm not saying that the cosmological constant is a negative pressure, but it contributes in exactly the same way to the dynamics of space-time as if there was a negative pressure, assuming that lambda is positive. So the first thing we notice is the cosmological constant acts as if it were a positive cosmological constant, acts as if there were a positive contribution to the energy moment, to the energy density, and it also provides a negative contribution to the pressure in the energy momentum tensor. But the same argument goes also the other way around. If we look at the 0, 0 component and the II components of the Einstein equation, we can also say that, well, T naught naught can mimic the behavior of a cosmological constant, right? I mean, lambda can mimic T naught naught, or it can mimic a TII, but it also works the other way around. The dynamics of space-time doesn't know whether a contribution on the right-hand side came from that term or that term. It just cares about the sum or the difference of the two here. And that's interesting because when you look at the contribution that the scalar field makes to the energy momentum tensor, you see that the energy momentum tensor has a contribution from the time derivatives of the field, which is like a kinetic term, 1/2 v squared. So the energy momentum tensor of a field has an energy contribution that's proportional to 1/2 phi dot squared, and a pressure contribution that goes this way. But the potential of the scalar field also contributes to the energy density and contributes to the pressure. And interestingly, it contributes in exactly the same way that the cosmological constant does. The potential of a scalar field, and that is what makes scalar fields so important in early universe cosmology, the potential of a scalar field, but not of other fields, the potential of a scalar field is such that if there is a large value of the potential, it will increase the energy density but decrease the pressure by the same amount. And if you look at the extreme case, where the potential is much larger than this, therefore much larger than that, then the energy momentum tensor has some positive value for the energy density and a corresponding negative value for the pressure, exactly as if there were a cosmological constant. That's going to be very important because it means that while the cosmological constant by its very nature is a constant, a potential, of course, can change in space and time. But the potential has the capability of mimicking the exact same effect on the dynamics of space-time that the cosmological constant has. It just has to be much larger than the 1/2 phi dot squared. Now, of course, not completely the full story because we neglect other terms already here. We assumed here that there are no space derivatives. Everything is constant in space. In principle, there would be space derivatives too. Okay, so when the potential is dominant over time and space derivatives, then the potential will contribute to the energy momentum tensor in exactly the same way that a cosmological constant would. And the significance of that we'll get to in a moment. Let us consider a quantity that tells us how close we are to that scenario where the V dominates over that, and therefore how close we are to the scenario where the V is mimicking a cosmological constant. And we simply measure that by taking the quotient of the two. Right? You see, consider the contribution, consider the pressure. Sorry, this is the energy density here, it's T naught naught. Consider the energy density and consider the pressure. Okay? We want to know how close are we to having the dynamics of a cosmological constant. Well, what we can do is this. Let us consider what the cosmological constant would do if it were dominant. Well, then we would have that the right-hand side here is dominated by lambda. This is negligible. The right-hand side here is dominated by minus lambda. The ratio of energy density over pressure is therefore approximately -1. And so similarly here, if we take the energy density divided by the pressure, then if that ratio is close to -1, it indicates V is dominant here. If V was small, the ratio would be about 1. If V is large, the ratio goes to -1. So we can, there's a benchmark basically, there's a quantity, the ratio of the two, of energy density over pressure, which tells us how close we are to the usual regular behavior of relatively small potential, or how close we are to the extreme behavior of an effective temporary cosmological constant, a behavior that is characteristic for very large values of the potential. So we measure how much the potential is larger than the kinetic term by calculating this parameter W of t, which is the ratio of pressure to energy density, which is also known in chemistry as the equation of state, the ratio between pressure and energy density. So that's the kinetic term minus the potential divided by the kinetic term plus the potential. And the thing to remember here is that if W comes out to be -1, or whenever W is close to -1, then the V of phi not only dominates over the kinetic terms, no, it means that the universe will expand as if there was a cosmological constant. Now remember what we want to describe here. We want to describe a period in the very early universe in which it expanded almost exponentially fast. It turns out that a period of time in which the cosmological constant dominates the energy momentum tensor, or indeed the potential dominates the energy momentum tensor, such a period of time will induce such an exponential growth period. Easy to see. Let us consider the 0,0 component of Einstein's equation. Here it is again. Now imagine that the cosmological constant dominates, or indeed in T naught naught the potential dominates. But for simplicity, let's for now just say, let's say the cosmological constant dominates in this. Well then, this equation, having neglected this part, this equation reduces to a dot over a squared is equal to 1/3 lambda. Or a dot over a is the square root of this, where this is a constant. In other words, a dot is proportional to a, which means that a of t is an exponential. Namely, a of t, the scale factor, has to be a naught times e to the power ht when the cosmological constant dominates, where the exponential increase coefficient is square root of lambda over 3, which is of course also what we earlier called the Hubble constant. So a cosmological constant, a large cosmological constant of value lambda, produces an exponentially expanding universe with a Hubble constant with a value of square root of lambda over 3. Now we do have a cosmological constant in nature, so it seems that this is a good way of describing perhaps the very early universe and its exponential expansion. But there are two fundamental problems. The cosmological constant that is currently observed in nature is too tiny. It's like 122 orders of magnitude smaller than the Planck scale, but we would actually need something that's close to the Planck scale to have the kind of dramatic expansion that we would need for the very early universe. So the cosmological constant that we observe cannot be the cause, cannot have been the cause of the almost exponential expansion in the very early universe. After all, it is a constant, and so it couldn't have taken a different value earlier.
So up until now, we've had like all these things that are indistinguishable between potential and cosmological constant. So this value we're measuring here, is there a way to distinguish that value from the value of the potential currently?
Very good question. It could be that what we now talk about as a measured cosmological constant is really also the potential of some field. It could be, absolutely, and there's much work on that. It's just that we don't really have positive evidence yet that it really is, and it's so much easier to just postulate a constant than to postulate fields that at the moment it is more efficient conceptually to just say it's a constant. But yeah, we're definitely looking for evidence to see that it's a field. Also conceptually, it's just so much, it would be so much more satisfactory to be able to say the cosmological constant is 0. Because it's very difficult to understand why it would take a very small value. The cosmological constant has contributions from the vacuum energy, from the ground state energy of all the modes of all quantum fields. And they would canonically give you 122 orders of magnitude more in a cosmological constant than what is observed, and therefore it just seems much more likely that there is some deep reason that sets the cosmological constant equal to 0, rather than just very, very, very tiny, like 0.0 and then 120 zeros and then something. What would make it so small? So yes, it is possible that we don't have a cosmological constant, and that what we currently see causing the slight exponential expansion of the universe is also due to a scalar field. Could be. In any case, the acceleration that we observe today is nothing compared to the acceleration that is needed, that we need to describe as having happened in the very early universe in order to be able to explain the various things that inflationary cosmology can explain. And also, if we postulated that the current day cosmological constant were responsible for the very early universe inflation, then we would run into a fundamental problem, which is that a constant is a constant. It never stops doing what it does. And so if the very early universe inflation was caused by a cosmological constant, well, it would never end. It's just always there. So the very early universe inflation had an end, obviously, so it cannot have been caused by a cosmological constant. The present-day acceleration of the universe may never end, and therefore it may be caused by a cosmological constant. So here's a realistic possibility then for the inflation in the very early universe. It could be that the cosmological constant was 0 or small in the very early universe, and therefore at all times, but the expansion was caused by a temporarily very large potential V of phi. This leads to one of the biggest ideas of science ever. Namely, the idea for the origin of the universe in cosmic inflation. Consider a universe like ours. Everywhere, at all times, all the quantum fields quantum fluctuate. It's usually not easy to see, but with modern experiments you can measure these things readily at sufficiently small scales. Now, it can happen as a rare fluke that a scalar field, let's call it already the inflaton field, quantum fluctuates in a patch a few Planck lengths across with a very large amplitude. Of course it does quantum fluctuate, but very large fluctuations, both in size and in amplitude, are suppressed. They're very, very unlikely. But imagine that for a patch a few Planck lengths across, the inflaton field fluctuates in such a way, fluctuates to such values of phi, that the V of phi, the potential in that patch, is almost as large as the Planck scale, as the Planck energy. What would happen then? You see, if the fluctuations are of regular size, of likely size only, then when the potential is a little bit elevated because of a fluctuation of phi, then you could imagine that this stretches space-time a little bit. Because it's as if you had, a little bit of a cosmological constant mimicked here. Contribution to the positive energy density and negative pressure, and we just discussed what it does to the space-time. It makes it expand. So whenever a scalar field fluctuates, it makes space-time underneath it also fluctuate, and it makes it fluctuate in such a way that it tends to expand a little bit. But usually these fluctuations happen and they leave no trace. They will just basically snap back until the next fluctuation happens. But now imagine that as a rare fluke, we have that a fluctuation of phi takes a large amplitude of the potential in a patch of significant size, a few Planck lengths across. And also spatially homogeneous. We don't want space derivatives of the field to mess up our argument in a moment. So all this adds to the unlikeliness of this to happen, but it can happen as a rare fluke. Then what will happen? Well, in this patch then, the equations will have a V of phi dominating the energy momentum tensor, which will impact the A of t. So locally, we will have an expansion. And if the V of phi is large enough on a sufficiently large patch, then that little patch can grow exponentially. And if the V of phi is large enough, the coefficient of the expansion can be dramatically large. So what we would have is that from a tiny patch, which could be right here, right now, a whole new universe could mushroom out of it. And it doesn't take much time for this to happen. So in this way, a mother universe could spawn a daughter universe, and of course that universe could end up being a universe like ours, which could then again spawn daughter universes and so on. Of course, very little is known about that exact phase where you would have this mushrooming out, the very beginning of that phase, that spawning of a daughter universe. And there's much speculation about how extreme that event is. For example, is it extreme enough so that it can retune what the constants of nature are? So for example, the fine structure constant in our universe, it's like 1 over 137. But if our universe spawns a daughter universe, is it guaranteed that that daughter universe would have that same value? After all, the universe would undergo some pretty dramatic things. Not only would it mushroom out at such an extreme rate, but the fluctuation at the beginning is certainly something very nonlinear. So if the constants of the standard model of particle physics have some dynamical degrees of freedom that may be hard to excite, that's why they look so constant to us. But if they are actually dynamical, chances are that that kind of event might detune it. So you could have a whole evolution of universes where universes spawn daughter universes with various constants for the cosmology, for the constants of their particle physics. So you could have some daughter universes that are conducive to life, others are not. In some universes you would have that stars, for example, burn much faster. In others they burn too slowly. In some you can't have sophisticated chemistry, and so on. Anyway, we can't really calculate through this nonlinear regime here, but it opens up such possibilities. Now here's an example potential that could achieve such a thing. So remember, we have a scalar field, the inflaton field. It has a potential V of phi. And let's say that the potential looks like this. These particular features, why these features are perhaps reasonable, we'll discuss in a moment. So if you have a scalar field with a potential like this, then the scalar field usually wants to hang around about here. It wants to have that kind of value. In fact, whether this value of phi is 0 or 27 doesn't really matter. What really matters for a field is what energy it has. So usually the field wants to hang around that value here. But quantum fluctuations can take it anywhere. The field's amplitude is fluctuating, and so in particular, the field's amplitude might be fluctuating such that it ends up here, the amplitude. Normally that's very rare, and it would fluctuate back very quickly, but it could be that it fluctuates to this value in a patch a few Planck lengths across, and in a homogeneous way. Again, a very rare event, but it could happen. In which case we end up here. That would be the beginning of the spawning of a daughter universe. The potential has to be very high up, so even though this may not look very high, this really ought to be close to the Planck energies over there. Not quite, but close to the Planck energies. We want that so that the expansion is suitably dramatic, suitably large. We will get into how large we need it to be. So what would be the evolution then? So imagine the field phi finds itself over here in a sufficiently large patch. Then that patch expands explosively fast. Remember, the Hubble constant would be the square root of V over 3. If V is very large, then that Hubble constant would be very large. So if the potential fluctuates in a small patch, a few Planck lengths across, such that it ends up here with the potential, then that patch mushrooms out very fast. And while it is expanding, the potential does what it wants to do always, which is the potential wants to diminish. Right? It wants to roll down that potential here. It wants to go back to the minimum position of the potential. Now it's going to be important that the potential is relatively flat for a while. We don't know that for sure, but the model requires that the potential actually has a kind of a plateau where it's not exactly flat. It has to have some tilt so that the field will move, the field's amplitude will move when it tries to lower its potential towards the minimum, but it will move slowly. This is what is called slow roll inflation. And then eventually, of course, it will reach the end of this slow roll phase, and then the field phi will approach its minimum, the value at which its potential is minimal relatively quickly then after that. And this is when inflation then ends, because once the field amplitude has reached that value, the potential is back at zero, and therefore it no longer contributes as if there were a cosmological constant. The universe has no longer any reason to expand exponentially, and instead this is where hot Big Bang would start. So we would have our mother universe mushrooming out this daughter universe, and when the mushrooming ends, when the field value approaches that value where the potential goes to zero, then there is no longer a mimicking of a temporary cosmological constant, and the universe will still keep on expanding, of course, but in a decelerating way. Now you may wonder, why a hot Big Bang from that point onwards? Why hot? Shouldn't it be dramatically cold? After all, if the mother universe had stuff in it, then after this dramatic expansion, where from a volume of a few Planck lengths across, which cannot contain much, I mean, there won't be many particles in there, and from a patch that was just a few Planck lengths across, you would get a huge universe, gazillions of light years across, then whatever was in that initial patch would be diluted to that extent, so we can pretty much say the universe is empty. So how could it be that the usual Big Bang cosmology of the textbooks kicks in at that point in time, when that's reached? Well, it kicks in because when the inflaton reaches slowly that equilibrium point for phi, where the potential is vanishing, then the potential goes down, but the potential goes somewhere. It has to go somewhere. That energy has to go somewhere. And that energy goes into the production of particles. The inflaton field is assumed to have vertices, Feynman graphs, Feynman rules, with all the other particles, or at least with some of them. And so as the inflaton potential decays, we have, in effect, inflaton particles decay into all kinds of particles of the standard model. So that all that energy ends up producing a universe that's very hot at the moment that inflation ends. So then we have a hot matter-filled universe that then just cruises. It lost its engine for acceleration because the potential is no longer high. Notice too that what this means is that we were created out of an event of dramatic non-energy conservation. You see, the initial fluctuation that made the daughter universe mushroom out of the mother universe, that initial fluctuation had just a patch, a few Planck lengths across where the potential was elevated. Energetically, that's very cheap. It doesn't cost much energy, right? But that patch then expanded to billions and billions of light years across, while keeping the potential the same. So that was a huge magnification of the amount of energy that there is. And it's not really miraculous. Remember that in general relativity, there is no such thing as energy conservation. For example, a cosmological constant is an energy density. It makes the universe expand, but it's a constant. The energy density of a cosmological constant does not dilute. And neither does the energy density of a scalar field. It does not dilute when the universe is expanding. Remember, we are used to thinking in terms of energy is conserved. Of course, energy is conserved. Yeah, energy is conserved. Yeah, but why is energy conserved? It's conserved because in usual daily physics, we have time translation invariance. By Noether's theorem, that amounts to energy conservation. We don't have any time translation invariance in general relativity. Not with such, the space-time itself is time-dependent, and all of that means that there is no, you can't use Noether's theorem to derive energy conservation. It's not conserved. And there's no killing vector field, and no time-like killing vector field that would save it either. Okay, so concretely then, it looks like this. The Klein-Gordon equation, I just wrote down the Klein-Gordon equation again. This is the Klein-Gordon equation for the inflaton field under the assumption that there are no space derivatives. Under the assumption that we have complete homogeneity in space, no space dependence. Right? We're still looking at that very simple case. We have that space-time itself is completely flat in space. The metric depends only on time, but not on space. And also the inflaton field, we still assume to be completely flat in space, completely constant in space, only dependent on time. So then that's the Klein-Gordon equation for it. Remember, there's the friction term, but there are no space derivatives. And of course, that's like the force here, right? dv by d phi, second derivative, and that's like a friction term, a velocity-dependent friction term. So the physics of the dynamics of the phi field, of the inflaton field, under this approximation of constancy in space, is really the same as the physics of a ball rolling down a potential or sliding down a potential. See, the acceleration of it downwards is given by the force that pulls it down, dv by d phi, and then there's also a friction term in this. And it's clear what this is going to do. It's going to roll initially very slowly, and then eventually it slides down much faster. I shouldn't say rolling because that would imply that there's some sort of rotational energy in it, and of course we're not modeling that. So there's some object that slides down that hill. Initially, slowly, and then eventually quickly. So the minus dv by d phi acts to pull phi down, and the other term is a friction term that slows that process down. This scenario, where initially it rolls down slowly and then fast as the end of inflation is approached, that kind of scenario is the most popular in inflationary cosmology, and it's called slow roll inflation because it has that period of slow roll. You see, the slow roll period is going to be important because it is during that slow roll period, during that period where we have effectively a large cosmological constant, it is during that period where we have the quasi-exponential expansion of the universe, that the quantum fluctuations of very small scales were amplified, were stretched along with the exponential expansion, and those, the quantum fluctuations imprinted themselves then onto that primordial gas that was present at the end of inflation, arising from the energy in the inflaton field. So it was during that slow roll period that quantum fluctuations were amplified so much. And you can see here a subtle thing which is that the expansion of the universe, according to that model, should not really have been exponential. Because if the universe had expanded exponentially, it would have meant that the Hubble constant would have been a constant. So that we just have e to the power ht as the scale factor. But if the potential is decaying slowly, and we surely need that for the ball to eventually come back, if it has some slope, it means that initially the potential was a little higher, later the potential was a little lower, which means that initially the inflation, the expansion was a little more dramatic, and then eventually the expansion slowed down a bit before it really came to an end. So what we would expect is that modes that were amplified earlier were amplified more, and those that were amplified a little later, the smaller modes, were amplified a little less. And there is already some experimental evidence that indicates that this is actually the case, which is supporting evidence for the idea that there was a period of slow roll down. Okay, so it's slow roll inflation. So during this slow roll inflation, the idea is that the potential V of phi dominated over that kinetic term 1/2 phi dot squared. And that also means that this equation of state parameter W, which is the pressure divided by the energy density, was approximately -1 temporarily during the slow roll phase. So you see in this picture here, we would have that the W parameter pressure divided by energy density is approximately -1 here, and then it becomes -0.9, -0.8, and then eventually it reaches some regular value. For example, when an electromagnetic field dominates the whole thing, then the equation of state parameter becomes 1/3. It's only a scalar field that drives that is such that when it dominates the energy momentum tensor, it drives it towards an equation of state parameter of -1, and therefore the universe to dramatic expansion. Okay, so let's see, do we get temporary exponential inflation from this? Well, let's see. The 0,0 component of the Einstein equation is this, and during the slow roll period, we can approximate it as that, because this is a small value from today's measurements. The T0 term is dominated by the potential, so we have that A dot over A squared is given by this during the slow roll period of inflation. Where, because it's slow roll, phi is not really much time dependent, neither is V. And therefore we have that A dot over A is approximately a constant. Not really, because we're slowly rolling, but it's approximately a constant. Which means that A of t is approximately given by an exponential expansion. But not quite, because the V of phi really is time dependent. So it's not really just A0 times e to the power t, and we will get later on a better approximation to what was really going on. But it's clear that indeed the potential V of phi can induce an almost exponential expansion, where V, or 8 pi g over 3, no, 8 pi g V plays the role of the cosmological constant. So during slow roll, we have effectively a slowly varying Hubble parameter. But it's a parameter now. It's no longer a constant. If the cosmological constant is all there is, then you get a Hubble constant and exact exponential expansion. But if what's going on is a potential and the potential is slowly varying, then you don't get a Hubble constant. You get a Hubble parameter value that's changing over time. So the expansion of the universe, A dot over A, is not a constant, but it's slowly dropping. And so we have h of t, a time-dependent Hubble parameter. The special case where h is a constant is, of course, just the de Sitter universe case that we had earlier. And in slow roll inflation, this is what we have from the equation above here, right? From here, we can read off that this plays the role of h of t. So h of t is given by this, where the phi depends on time. So what we see is that as the potential slowly decreases, as the inflaton potential, as the inflaton slowly approaches the value where the potential vanishes, also the Hubble parameter decreases and the universe accelerates less dramatically. Now, I used the term slow several times, but remember that all of these things happen in less than 10 to the minus 30 seconds. So slow is relative. It's just slow relative to what it could be if the potential was more steep. Okay, so again, inflation, the theory of cosmic inflation therefore predicts that the quantum fluctuations, the size of the quantum fluctuations of the field decreases for later and later horizon crossing modes. So modes that start out smaller will cross the horizon later, but by that time the horizon is already larger, the quantum fluctuations are smaller, and therefore smaller quantum fluctuations are baked in or are frozen in. So the later a mode is, the smaller a mode is, the less it has been amplified. That's a solid prediction of inflation. If any evidence to the contrary were found, it would really put the theory in trouble. But the evidence seems to support that. Okay, so then at the end of inflation, I think I mentioned it already, is when the potential drops, and then we enter into a period of reheating. So actually it won't just sit there like an overdamped harmonic oscillator. It will actually not be quite overdamped. It will oscillate a little bit before it settles. And one can prove, it's complicated, but one can prove that in this process, the energy that was in the potential indeed gets transferred into the production of all sorts of particles. Mathematically, what's behind it is that the harmonic oscillators of the inflaton field coupled to the harmonic oscillators of all the other fields in both a driving and a parametric way through gravity, and this will, through parametric resonance and driving, produce a hot gas at that point when inflation ends. So as I said, that's the beginning then of the usual traditional Big Bang scenario. Now, all of this argument, all of what we discussed so far, was about the zero mode. It was about, what we discussed today so far, was about just the constant part of the inflaton field, just the spatially constant part of the inflaton field, and just the spatially constant part of the metric. The universe is not that boring. There is stuff in there, and so we should describe also the structure in it. And of course, that's what we've been building up to all throughout this course. So let's look at quantum fluctuations during cosmic inflation, during that scenario here. Our strategy will be this. We will use a suitable potential, maybe we can think of it as looking like this, and suitable initial conditions, as we discussed before, the field fluctuating into such a value such that the potential is large and then slowly rolling down. And we will assume solutions phi naught of t and a naught of t to the problem that we just discussed. Remember, when we looked at the spatially constant field and spatially constant metric, we obtained a Klein-Gordon equation and the Einstein equation were all simplified. And if you specify the v of phi and the specified initial conditions, you can calculate how the Klein-Gordon field is evolving and how the metric is evolving. And let us call these solutions phi naught of t and a naught of t. So a naught of t is the scale factor of the universe under the assumption that the universe is completely flat in space. And phi naught of t is the evolution of the amplitude of the Klein-Gordon field under the assumption that it is completely flat, completely constant in space. Or in other words, it's the zero mode of the Klein-Gordon field. And we assume we know those solutions. Let's say these solutions are given. We can calculate them for any scenario we want. We cook up a potential, cook up initial conditions, and we can calculate what phi naught of t is and what a naught of t is during the interval of slow roll inflation. So up here. During that interval, that's when the universe is expanding exponentially, or almost exponentially. Let's call the initial time t initial, the final time here, not there, but here, the final time. Let's call that tf, or in conformal time, eta I and eta f. So we'll study the quantum field theory of what happens during that stretch of time. And concretely, what we will study is the full Klein-Gordon field, which is given by its zero mode, by its constant part, phi naught of eta, plus what we will describe by a little phi, phi of x and eta, where the little phi depends on x. So this we assume to be a small thing, just a perturbation, but we allow it to be space-dependent. And we will make the assumption that this phi is small compared to that. It's just a perturbation. In principle, the field is constant, but there can be ripples on it. But, and this is now where we deviate from, or where we much generalize what we did earlier in the course. We will now take into account that gravity too, that space-time too, that the metric too will fluctuate in space. We cannot avoid that. And clearly we cannot avoid that because if the inflaton field, if the scalar field has variations, then that means variations in the energy momentum tensor, spatial variations in the energy momentum tensor. And those spatial inhomogeneities in the energy momentum tensor must trigger spatial inhomogeneities in the metric too. It wouldn't be consistent to neglect them. So by considering the fluctuations in the inflaton field, we also sign up automatically for having to consider fluctuations in the metric as well. Now, as always, in very early universe cosmology, we make the simplifying assumption that all we have to worry about here is the inflaton field. In principle, of course, the electromagnetic field, fields of quarks and gluons and so on, they all fluctuate. They all contribute to the energy momentum tensor, and they all mess with the metric, therefore. But the scalar field is doing the most. It's the dominant part of this, as we saw, because it's having the most dramatic impact on the energy momentum tensor by moving the equation of state parameter the furthest away from what it would otherwise be. It moves it all the way down to -1. So let us look at the energy momentum tensor of a scalar field. Here it is again, energy momentum tensor of the scalar field. We are no longer assuming the spatial constancy. It's the full energy momentum tensor. So any fluctuations in the field phi will contribute to the energy momentum tensor in this way, and therefore enter in the right-hand side of the Einstein equation, and therefore produce an impact in the curvature and the metric. In other words, when phi of x is fluctuating, because of the Einstein equation, also g mu nu of x must fluctuate. Yep?
So the way we get the energy momentum tensor due to the field phi, we consider the variation of the action of phi with respect to the inverse metric tensor, right?
Yes, that's right.
And we have a subscript kg. Does that mean where does the Klein-Gordon come into?
It's just Klein-Gordon, yeah. So in principle, the energy momentum tensor has a contribution from the Klein-Gordon field, but it also has a contribution from the electromagnetic field, from other fields, and so on. And we are dropping that. We're only looking at the contribution from the scalar field now.
Right. Okay. But then, so the stuff that gets plugged in there, it doesn't come from Klein-Gordon. It's just variation of the action. It's 15.
Same thing. Same thing. I mean,
oh, I thought it was like a separate. The Klein-Gordon was like a separate differential equation, which.
No. Remember that the energy momentum tensor is obtained by differentiating the action of all fields with respect to the metric. So there will be a contribution to the energy momentum tensor from the Klein-Gordon field and from all the other fields as well. And this is the contribution from the Klein-Gordon field, and it will be in here. And it's the only one that we consider. Okay. So what we just concluded is that if the phi is fluctuating, then its contribution to the energy momentum tensor will fluctuate, and that will mean that the g mu nu is fluctuating accordingly. Is the opposite also true? Imagine that the metric is fluctuating, and we should expect that it too can quantum fluctuate. We will calculate it later. Then shouldn't those quantum fluctuations also produce quantum fluctuations of the scalar field? Yes, they should, but not all of them. So the metric has more degrees of freedom than phi. There are some degrees of freedom of the metric that are coupled to phi and some that are not. And we will have to disentangle the two things. There are some degrees of freedom that are closely linked. Some degrees of freedom in the metric are closely, or 1 degree of freedom in the metric really, is closely linked to the degrees of freedom to the degree of freedom of the Klein-Gordon field. But there are parts of the metric that fluctuate completely on their own. And they're not coupled, I mean, not to first order anyway, but they're not coupled to the Klein-Gordon field. Okay, so we have to consider small fluctuations in the metric. Here's how we describe that. The metric tensor depends on both space and time, really. Now, it consists of our early approximation, which was a metric tensor that is spatially homogeneous, that was just the plain FRW metric tensor in conformal time and conformal time and co-moving coordinates. The metric tensor looks simply like this for FRW spacetimes, but FRW spacetimes don't allow for spatial variation. So we add to the metric tensor some small perturbation. The gamma mu nu is a perturbation to the metric that allows it to fluctuate in space, well, and in time. So we assume this to be small. Perturbation theory in general relativity is a messy business, though. As you can imagine, because it's highly nonlinear. Another way to look at it is that this condition is not covariant. See, you change coordinate system, and then you can make this thing small or large. You can make components of a metric small or large, whichever way you want, by changing coordinates. So perturbation theory in general relativity is very hard. This can be controlled, but it took about 20 years to do it. 20 years of wrong papers until eventually the right papers were developed. I think they settled it in the 80s or so. But eventually, it's just a justification for why this actually does make sense, even though you can apply diffeomorphisms. It's just a justification and explanation exactly of what is meant by that smallest condition. So we would like to solve, of course, the full quantum theory of both the fluctuations of the metric, which means the fluctuations of the gamma, and of the phi. But this is way too hard, and it's not just too hard. It's not that our computers are too slow, it's that we don't even know how to start with it. There are infinities in there, which can be what is called renormalized, but the renormalization is ambiguous, and you have to fix certain renormalization conditions. Now, for a well-behaved theory, such as QCD, the number of renormalization conditions is finite. You can fix them with a few experiments, and then the rest is prediction. But with gravity, there's no end to how many renormalization conditions you would have to pose. So we don't really know how to quantize gravity. Now, in lowest order perturbation theory, we have that the metric is simply the constant metric. It's constant in space, but varying in time. And the inflaton field is simply the time-dependent inflaton field that is constant in space. That is our lowest order approximation. And then we will be interested in the first order that goes beyond that. So we will keep these, to be precise, we will keep these lowest order calculations classical. And then we will look at the first order perturbation away from that, the small perturbation of the inflaton field, space dependent, a small perturbation from the flat metric, that is space dependent. These we will quantize. Those we cannot really quantize because these were solutions to nonlinear equations. And it would be hard to quantize those. But in any case, it should be a very good approximation to consider them classical because their values are large compared to their quantum fluctuations. So it's totally reasonable to just consider a background metric that's classical, a background inflaton field that's classical. So the inflaton field that caused the exponential expansion of the universe, we will keep treating classically, just like we will keep treating the background metric that's constant in space also classically, just to describe the basic background on which everything happens. And then the space-dependent perturbations, phi of the inflaton field, and the space-dependent perturbations, gamma of the metric, these we will quantize. They are small, and here the quantum fluctuations are all that matters, because the expectation values are zero. Expectation values are zero because that would be the lowest order contributions. So for them, only the quantum fluctuations matter. So how does this approximation help us then? Yeah?
But do we consider that the two fluctuations are independent?
Ah, very good. No, we won't. It would be tempting to do so, but as we will find out, they cannot be treated as independent. It turns out that there are some fluctuations in gamma that are coupled to the fluctuations in phi through the Einstein equation. So we will have a combined degree of freedom in phi and gamma, and on top of that, we will have separate degrees of freedom in gamma as well. Basically, the metric has a scalar component to it, and that will be coupled to phi, but the metric also has truly tensorial degrees of freedom, and they will not be coupled to phi.
So really we just have, yeah.
Yes, but it would be different if there were no phi. It's actually the scalar part of the metric will combine with the Klein-Gordon field into one degree of freedom, where by a so-called choice of gauge, you can make it look like there's only gamma. By another choice of gauge, you can make it look as if there was only phi. But reheating at the end of inflation will actually break that gauge invariance, as we will see. Okay, so we make the appropriate approximations then. In principle, we have to put our ansatz that phi is the bulk phi, that's constant in space, the zero mode phi, plus the perturbations, and the similar for the metric. We have to put all of that into the full action and then expand it. And it would be very complicated, but we keep just the lowest order terms, just the quadratic terms in the action that are induced in this way. And what that means is that we will get pretty nice equations of motion for phi and for gamma, because we just take the lowest order perturbation away from the constant part. And that gives us equations of motion, we'll do them in more detail later, that are free, non-interacting quantum field theories for phi, and the free, non-interacting quantum field theory for the gamma, except for this link via the Einstein equation between some degrees of freedom there. And all the non-triviality in the quantum field theory of the phi and the gamma stems from the background evolution of phi naught and A naught. Remember, they will be classical. They give us the background on which everything is happening. Now, we should expect several sources of non-triviality. I really anticipated it all already, but let me just mention it. So one point is that there is some interdependence between the perturbations of phi and of gamma, as we said, because of the Einstein equations. The scalar part of gamma couples to the scalar field phi, and that goes vice versa, but there are degrees of freedom in gamma that are not scalar and therefore completely decoupled. It's the non-scalar degrees of freedom that there was so much excitement about when the BICEP collaboration claimed they had seen gravitational waves. That would have been an observation of inhomogeneities in gamma that are not linked to phi, that would have been purely quantum gravitational fluctuations. Unfortunately, it was probably foreground that they saw. Okay, so how do we understand this thing about gravity, the metric, having some scalar part and some non-scalar part? What do we mean by that? Well, remember that gravity has some similarities with electromagnetism. It's kind of a grown-up version of electromagnetism. It's more sophisticated, but it has some close similarities. So electromagnetic fields, very important, you can separate them into two kinds. And I'm not talking about the distinction between electric and magnetic fields. No. Electromagnetic fields have components that have contributions that are there because there are charges and currents that created them. And then there are electromagnetic fields that freed themselves from currents and charges. They can exist even in the vacuum. Some contributions to an electromagnetic field can only exist where there are charges and current densities. But others can exist also in free space, also known as electromagnetic waves. But it's a bit more than just electromagnetic waves. So some electromagnetic fields only exist because of where there are charges and currents, but there are also electromagnetic fields that are self-sustaining, that exist independently, that exist with their own dynamics. And concretely, it works like this. Consider, for example, an electric field. You can always decompose the electric field into what might be called a scalar part and a part that might be called vectorial. I hope you remember this. Any vector field can be decomposed into a gradient part, which is to say it's the gradient of a scalar function, and into the rest, which one can show is the curl of a vector field. And in that sense, the first part is scalar because it has only as much degrees of freedom as a scalar field. It's the gradient of a scalar field. Whereas the second part is really truly vectorial because it's the curl of a vector field. You need a whole vector field to describe this thing. So the scalar part is the gradient of a scalar field, and the vectorial part is the curl of a vector field. And you can show, it's purely differential geometry, it's not really physics, you can show that on mathematical grounds, that a gradient field has no curl, and that vice versa, any of those curls doesn't have a divergence. So you can recognize the two components this way or that way. And then according to the Maxwell equations, the scalar part of the electric field is actually tightly linked to charge densities. It can only exist where there's a charge density. So the divergence of the electric field is the charge density rho. Whereas the vector field, the truly vector part of the electromagnetic field is given by minus dB by dt. This is the self-sustaining part of the electromagnetic field, the part that can live also in the vacuum. You know, electric fields decaying, inducing magnetic fields decaying, inducing electric fields, and that's how you get traveling electromagnetic fields. Very similarly, some curvature of space-time can exist even where there is no matter. The energy momentum tensor is 0 and still space-time can be curved. And then there is some part of curvature which is not self-sustaining, which requires there to be energy momentum tensor density. Now the self-sustaining part contains in particular gravitational waves. So we should expect that the metric, or the thing that we are considering, the perturbation of the metric, we should expect that the perturbation of the metric similarly can be decomposed, just like the electric fields and the magnetic fields. And that can be done. There will be some curvature in that metric that is induced or induces the inflaton inhomogeneities, and some curvature inhomogeneities that are self-sustaining and independent of the fluctuations of the inflaton field. So how do we separate the inhomogeneities of the metric? Similarly to what we did with the electric field, decomposing it into a curl part and into a gradient part, we can now do the grown-up thing for gravity, and we decompose the perturbations of the metric now. Now it's more complicated because the electric field was simply a vector, was simply a vector field. And all it could contain was maximally a scalar part and a vector part. But the metric tensor is a two-tensor. It can contain a scalar part, a vectorial part, and a truly tensorial part. So this thing will decompose into three parts. So there will be three components. There will be parts of gamma mu nu, which can be expressed simply in terms of scalar functions. And then there will be a part of gamma mu nu, which you can express by specifying vectorial functions. And then there will be a part of gamma mu nu that is truly tensorial. It's not derivable by, let's say, differentiating a scalar function or differentiating a vectorial function. And it's only the first part that will be coupled to the Klein-Gordon field. So the decomposition of the metric tensor with respect to its spatial structure goes like this. The line element is just another way of writing down what the metric is. So the metric can be, the line element is expressed in terms of the metric in this way. We choose to work with conformal time and the co-moving coordinate system, of course. Then what we have is that we can decompose the metric, or the line element, into four parts. There is the FRW part, which has no space dependence. It has this non-trivial time dependence here. You know, that's just the usual. If this was absent, this would be simply the metric of FRW spacetimes in conformal time and co-moving coordinates. But we consider also perturbations in space, and we get the scalar, vector, and tensorial components. So we get a part of the line elements that's expressible in terms of scalar functions, vector functions, and tensor functions. And here they are. The scalar part of the metric, the scalar part of the perturbed metric takes this form. It's simply a list of all, it's simply the sum of all terms that you could possibly get from a scalar function that give you a two-tensor. So for example, so here we have the scalar part to the metric, and then we have here a scalar function and d eta squared. You know, this is contributing to the d eta squared term in the metric. And then we could also have another scalar function b, and the names are just, I just matched the names of the variables as they are found in textbooks like the one by Little and List. So the names don't really mean anything. This is certainly not a magnetic field. It's not an electric field. These are just some names for this function. So this is a scalar function. If you differentiate it with respect to I, then you get a spatial vector. And that spatial vector index, together with that spatial vector index, gives you something spatially two-tensorial. And then here you have a scalar function, you have another canonical construction, the canonical delta ij. And then finally, you have the possibility to just take a scalar function and differentiate it twice. And then again, you get two spatial tensor indices that you can contract with those. So these are all the possible terms that can give you a contribution to the metric and that are in terms of scalar functions. And then, how about vectorial perturbations of the metric? Well, let's look at it. We have here a vectorial component to the line element. And if V is some vector-valued function, then this index with that index contracts to give us a contribution. We can also have a W vector-valued function, and then together with this index, and we symmetrize that so that we get a symmetric contribution to the metric. After all, even the perturbed metric has to be symmetric. And finally, we are left with a part of the metric that's perturbed by a function that's truly tensorial, that doesn't have any scalar or vectorial part in it, in the sense that it cannot be written in a canonical way as expressions in terms of vectors and tensors and their derivatives. Now, remember how the gradient part of the electric field could be recognized by the fact that its curl is vanishing. And the curl part of the electric field could be recognized by the fact that its divergence is vanishing. So similarly here, we have conditions on those many functions that can arise in perturbations of the metric. Namely, we have that these functions Vi and Wi that enter in the vectorial perturbations have the property that this divergence is vanishing and that divergence is vanishing. And we have that the truly tensorial perturbations to the metric, the ones that cannot be expressed in terms of vectors and scalars and their derivatives, obeys that, well, it's symmetric, of course, because it contributes to the metric, which has to be symmetric, but it's also traceless, and it obeys this condition. And the fact that it's traceless, for those of you who are familiar with conformal transformations, describes so-called Weil curvature. Okay, so what we have now, so far, and this will be all for today, is that we said we are going to study the quantum field theory of the perturbations of the inflaton field, and we will study the quantum field theory of the perturbations of the metric. And that amounts to studying the quantum field theory of, in principle, those parameters, those unknown perturbation functions, the H. We will have to do the quantum field theory of H, quantum field theory of V, quantum field theory of W, and the quantum field theory, in principle, of all those scalar fields here, the scalar type perturbations of the metric. In principle, we have to do the quantum field theory of this phi field, the B field, the E field, and the chi field. Fortunately, we will not really have to do. We will not really have to study the quantum field theory of all of them. And the reason is that because the metric is tensorial rather than scalar, these functions are coordinate system dependent. Right? They're coordinate system dependent, which means that if you change coordinate system, then you change the values of those functions, which means that it's not the case that each of them describes a separate physical degree of freedom. Much of what these values are just choice of coordinate system. So what we'll do is we'll choose a coordinate system suitably such that we are left with just the actual physical degrees of freedom, and we don't quantize choices of coordinate systems, which wouldn't make sense. That sounds easier than it's done, perhaps. It took 20 years to do that properly. In any case, so this is going to be our strategy: identify which are the physical degrees of freedom of these perturbations, taking into account the arbitrariness in the choice of coordinate system, and then quantize those. We will have to write down the equations of motion for all of them, and we will then also have to identify how the choice of coordinate system, also in this context called choice of gauge, will impact the relationship between the inflaton field, which is scalar, and the scalar part of the metric there. That's a bit non-trivial. But overall, the message is that there's going to be one combined degree of freedom of the inflaton field and the scalar part of the metric. Of all those 4 functions, only one will survive after gauge fixing, and that one will actually be gauge equivalent to the inflaton field phi. Basically because the Einstein equation tells you that you cannot distinguish whether a fluctuation of the scalar part of the metric occurred and triggered a fluctuation of phi, or a fluctuation of phi occurred and triggered a fluctuation of the scalar part of the metric. It's really the same thing. And not 2 independent degrees of freedom, it's really just one. And then we will also see that the vectorial perturbations of the metric do not play a significant role in cosmology, but the tensorial part will. And as I said, there is a lot of effort, starting with Bicep and now with Planck and others, to try to measure the physical implications of that tensorial part. But we'll get to that. Okay, any questions? Well, if not, have a nice weekend.